Okay, so today's speaker is local from Bilkent University, Ergun Yalcin, and he's going to tell us about the date group for finite group and dimension functions. So thank you very much.
Thank you, Jian. So this is joint work. I'm going to tell it in a minute, but this is joint work with Matthew Gelvin, and this is about date groups of finite groups. But at the same time, it's about more G spaces. So it's topological, actually. A lot of our main proof is very topological, although we have to deal with a lot of algebra at the beginning about date groups and KG modules and module representation theory and so on. So there are two elements to this talk: a lot of module theory, a lot of module representation theory. But at the same time, we will be talking about more spaces at some point. I think I will start with definitions of, but let me mention again that this is joined with Matthew, and this is supported by some project. So let me start. There are three sections, actually. The first part will be about defining this date group. Can't see the top, but it's okay. You can see the title, right? You can see everything. Okay. So we'll be taking a finite group. G will be a finite group. We will always have a fixed prime P. And S also will be the notation for 0P subgroup of G. We will work over an algebraically closed field, P, characteristic P. We will only consider finite generated KG modules. So our modules will be over group ring, and they will be finitely generated. So there are two notions in module representation theory that are more accessible, sort of, to study the permutation modules. Because as you know, module representation theory is harder than the usual representation theory, and classifications are wild type and so on. So we can't do much, but the permutation module seems to be a little bit more accessible. So this talk in some ways is about permutation modules. So a KG module is called permutation module if it has a G invariant basis. So if you take the X as this G invariant basis, which is a G set, it's common to denote these permutation modules as KX. And G permutes to X, and you have a vector space with basis X. So this is sort of easier representation theory than others. Now, we will be looking at something a little bit more complicated called endo-permutation module. These endo-permutation modules have the property that if you tensor M with this dual, that you get a permutation module. And tensoring with this dual is same as taking endo-permutation KG modules. Like take the K endomorphisms as KG module. That's why it's called endo-permutation. Now in the green ring of KG modules with tensor product, these M's will be invertible objects, invertible elements. So endo-permutations are important in that sense. They're like units in the green ring of KG modules. But there are other reasons to focus on endo-permutation modules. One is you can maybe hope to classify them, understand them, much easier than entire all KG modules. Other is they also appear as, at this point won't make sense what I'm saying, but they appear as source modules of simple KG modules. So endo-permutation modules are important. So here's the example. If you take CP, cyclic group order P, and look at the kernel of the map, augmentation map from group ring of the CP to K. This is a P-1 dimensional submodule. And the common notation is omega s because it's like Heller shift on the first positive shift of k. This module, tensor with its dual, gives you k plus free. So if it's p minus 1 dimensional, if you tensor, you get p squared minus 2p plus 1. So that plus 1 is k. And the rest of it is p minus 1 copies of free modules, ks. So as you see, there's a k and free, so that's the permutation module. Free modules are already permutation modules, ks. So you get k plus a free module, which means that omega s is an endo-permutation module. These actually are very important examples for CP. These will be generate something called a date group. Later we'll see that. But these Heller shifts are primary examples. If you heard something called endo-trivial module, which I will define later, these are also endo-trivial. So k plus, if a kg module tensor with this dual gives you k plus a projective module, that's called the endo-trivial module. So this example is also endo-trivial module. Endo-permutation modules are generalization of endo-trivial modules in that sense. Okay, a little bit slow, but so a kg endo-permutation KS module is called CAP. So I'm focusing on P groups now, and I'm using S as the P group. Always S will denote the P group. So on the P group case, we talk about capped endo-permutation modules. And the cap means that M star tensor M has a trivial summand. So normal definition was this permutation module. It doesn't have to have a KSS, like trivial summand, but if we require that, the KS module is called capped. And this is some way to guarantee that things live on the top level, on the S level. So two cap and the permutation modules are equivalent if either M star tensor N is permutation, or you can say direct sum is an endo-permutation module. So these are equivalent conditions, and this gives the equivalence relation on capped endo-permutation modules. So basically, with tensoring, they should be dual to each other some way. So the date group of a P group is defined as the equivalence classes of capped endo-permutation KS modules. These capped ones, equivalence classes, and the operation is the tensor product. From the definition, you can tell that if you tensor two endo-permutation modules, they still will be endo-permutation. So that defines the abelian group operation. You have to check a couple of things like equivalence classes, like tensor product under equivalence class is still okay, well-definedness, and so on. You have to check also that this defines a group operation, well-defined. But the inverse will be the dual of the module. So that's why the condition comes, I guess. The inverse minus M is the class of M star.
Excuse me.
Yeah.
Sorry, in the definition of equivalent, is that really a plus, or should it be a tensor?
The first one is plus. The second
it is
one
a plus.
tensor.
Okay, right.
Yes. Yeah. So it's an odd thing to do, to define using the sum, but the sum doesn't have to be permutation. The sum has to be endo-permutation.
Right. Yeah. Yeah. Okay.
That's why you use the sum.
Yeah. Okay.
It's a good point. Thank you.
Thank you.
Okay, so the example we had before, CP, they generate this group, and if you're familiar with the projective resolutions of CP, CP has a periodic projective resolution. So in particular, if you take the Heller shift once and Heller shift twice, you get something K plus a projective. So that means that this omega S tensor with itself is K plus a permutation or projective, so its class is 0. So omega S tensor with itself as a 0 class, which means that as a abelian group, this is just the group integers mod 2. And there's no other generators in this case, like there's no other date modules, so you can verify that. There's no endo-permutation modules that is different than this one. For CP cross CP, it's a little bit more complicated. We again have Heller shifts that generates these date group. And in this case, there's no periodic resolution. CP cross CP don't have periodic resolution. So Heller shifts powers are not ever K plus projective. So that means they generate a copy of integers. And in the case of P equals 2, this is all you get. So those integers, this copy generated by omega S is the entire ds. For P bigger than 2, you get mod 2 classes also, which comes from quotients with maximal subgroups of CP. So there are exactly P plus 1 maximal subgroups, and each of these quotients gives you a CP. And for those CPs, you have also omega G over H or S over S, S over some CP. So for those ones, you get also endo-permutation modules, and they generate a the subgroup which is P plus 1 copies of C2 mod 2. And Z is still generated by the Heller shift, the first Heller shift. So these date groups, of course, computing them will mean like you're classifying all the endo-permutation modules. For P groups, this is a very well-studied area. There were so many papers were written, and there was, starting with date, actually. Tevenas and Carson has a couple of Invenciones papers on this topic. Eventually, that led to classification of endotrivial modules. And then Mazda has papers, and Serge Bouc has papers. So what people focused later, mostly this was, I guess, a paper by Bouc and Tevena did that. They focus on subquotients of P. And they realized that generators come from these subquotients, quotients of subgroups. So date groups of quotients of subgroups become generating the whole thing. Then they start finding relations among those subquotients, and that led to a notion of genetic sections. So genetic sections are subquotients or sections of the group, which have certain properties, and the date group for those sections sort of you can inflate and induce to all the date group of the whole group, and they generate the date group. So Serge wrote a very nice paper which can be considered as complete description of date group of a P group in terms of these genetic sections, and this published in 2006. Of course, it might be difficult to, for a given group, exactly say this is what the group is, because you have to understand genetic sections and how they're related. But it's still a very good description of what the DS is.
When P is equal to 2 in the first example, what happens then?
So in that case, the Heller shift of Kg, like so K. You have a map from Kg to K. The kernel is K because it's C2 action, and the field is characteristic 2. So the -1 action on the field becomes trivial. So the Heller shift is actually the same as K. So that means the generator is 0. The entire date group is 0.
Okay.
So it's a good question. That's exactly makes the P group in the second part also. That's why you don't get these pieces from maximal subgroups, because for date group of C2 is 0. If you want, I can try to, okay, just to show how this works. So when you have KC2 mapping to K, normally with ZC2 mapping to Z with augmentation, the kernel is what we call Z tilde. So this is generated by 1 minus G. Say C2 is generated by G. So this thing, when you act with G, you get G minus 1, which is minus of the generator. So that's why it's Z tilde. But when you're working over field with characteristic 2, the kernel, the K tilde is same as K. So this Heller shift, C2, is isomorphic to K. That means its class in the date group is the class of K. K is 0 in date group. So the generator becomes 0. So we can conclude that DC2 is just 0. There's no non-trivial date endo-permutation module except from K. K is the 0. K is the 0 of the date group for all groups.
Excuse me.
Sure. Yeah.
Can you say anything simple about something like the quaternion group? I mean, which is periodic. So
yes, you can say Q8 will have a generator of order 4 because of the periodic
right.
space.
Oh, okay. So is that's so that's it? It's cyclic of order 4, or are there more?
Will be for Q8. I believe there is a C2 cross C2 as a subquotient.
Yeah.
Right. So
Right.
there will be a generator coming from that too.
Right. So,
okay. Every subquotient, the potential can give you some classes.
Right, but you get this nice 4 periodicity.
Yeah. Z4. Yeah.
Oh, great. Yeah. Thank you.
Okay, so this talk is about extending this to finite groups, but in finite groups, many things are much more difficult, right? You first of all will have in the P group case, when you're looking at a transitive G set, G over or S over U or something, a transitive S set, and the P group case, K of that set is indecomposable as a KG module. But for finite groups, when you take a transitive G set, say G over H, KG over H can be decomposable, may decompose. There are many examples of this situation, of course, but one example I wrote here with S3 moda C3 and prime 3, this is KC2 decomposes as K and plus K minus 1. So these decompositions make the indecomposables not just permutation modules. So that is one problem. There are other problems too, but I will. So instead of studying with permutations, one should work with P permutation modules. These are summands of permutation modules. So permutations modules should be replaced by P permutation modules, which are defined as summands of permutation KG modules. Thankfully, there is a different description to these P permutations, I will say in a minute. But Then you define endo-p permutation module as a module who is end or m star tensor m is a p permutation module. So everything becomes p permutation. So what I said before, a kg module is p permutation. Something is a summand of kg or h. If and only if it's restricted to 0p subgroup is a permutation KS module. And this is easily proved by induction. So endo-p permutation modules also can be specifically described like that. Something is an endo-p permutation module. If it is restriction to a 0p subgroup, is an endo-permutation module. So one will think that if we're describing them as something that is restriction to modules is, and you should check the time, is endo-permutation, then it's a good idea to use these restrictions also to classify them. This was done by Urfer. But before I talk about Urfer's work, I should say a couple of things about the common kind of terminology about KG modules. So KG modules can be like summand of induced module from a subgroup, and this the smallest such subgroup is called vertex. And there are these vertices. The vertex is not unique, but they're unique up to conjugation, G conjugation. And by the characteristic being P, you can easily show that the vertex should be a P group. Otherwise, you have a smaller one. So minimal such subgroup where M is a summand of an induced module from some subgroup is a P group and is unique up to conjugation. Now, if you are dealing with an indecomposable module, then this induced module will be induced from an indecomposable P module, some P subgroup. This module that you're using to induce it is called the source. And again, it's unique up to actions of the normalizer and so on. So all the p permutation modules, where summands of permutation modules, are actually trivial source modules. So another name for these modules are trivial source modules. And many classification attempts for trivial source modules has been done, and there are rings you can define and so on. But we will be doing something slightly different. So this is Urfer's work. Urfer did this. Urfer is actually a student of Jacques Thévenin, and this is mostly his thesis work from 2013. And he studied the p permutation modules by looking at its sources. So those actually modules where you can view M as a summand of induced module. So these sources have to be endo-permutation modules, and they have to be capped if the original module is capped and so on. So you can define a equivalence relation on endo-p permutation modules by looking at the equivalence relation on source modules as date, like elements in the date group, because sources are in the p group, like live as a p modules where p is a p group. So this way, you can actually classify endo-permutation modules up to some equivalence, but this equivalence is very strong. Like the many modules that shouldn't be equivalent becomes equivalent. So it's a little bit too coarse to classify endo-p permutation modules under this equivalence. Lassueur later, she's also a student of Jacques Thévenin, and this is also most of her thesis work. She did a different approach. She looked at the certain special type of endo-p permutation modules, and she defined equivalence on them. And this special subclass is the modules where M tensor M star is not just a endo-p permutation module, but they're also in this special form. So this special form, of course, is a endo-p permutation module, but it's more than that. It's almost like endo-trivial definition, like K plus projective, if you remember in the trivial definition at K plus projective. Here you have K plus something which is projective relative to non-zero P subgroups. So it's a slightly, this is basically a relative version of endo-trivials. This is a subclass of endo-p permutation modules, and she defined equivalence class on them. So these are called strongly capped endo-p permutation modules.
By relative, do you mean restriction to those?
Yes, yes. Relative in the sense that it's some amount of things induced from there. So relative projectivity with respect to one will be normal projectivity. But now you take relative projectivity with respect to non-zero P subgroups. So Lassueur defines a Dade group. She studied that, the group that she defined. So there's a relation between her Dade group and Urfer's Dade group, which will come up later. They're not same, of course. This has more core, like things are not identified as much. So Dade group Lassueur defines, surjects on the Dade group Urfer defines, and there will be a kernel which has a lot more modules, a lot more classes. So it's a better definition. But Urfer computes tensor induction. So because everything is defined by tensor products, induction in the Dade group theory should be tensor induction. She calculates tensor inductions of her strongly capped endo-p permutation modules. And she finds that their tensor induction is no longer strongly capped, which is a problem because then you can define induction on the Dade group. So because of that, people sort of stopped working on this and thinking that maybe there should be a different definition. So more sort of including maybe more modules than the subclass, more endo-permutation modules, endo-p permutation modules, which will allow the tensor induction also to be defined. So we looked at this and we said, what is wrong with Lassueur's definition is that she, first of all, assumes that n is k plus something, but in the original definition of Dade modules, you allow direct sums of k. In the P group case, n can have many copies of k. So we said, can we extend it at least by putting an n there? So this is our definition with Matthew. We say a kg module is a Dade kg module if there is an n such that n is k to the n plus w, where w is again, which has some n's whose vertices are non-zero P subgroups. So this M is endo-P permutation module, definitely, but it's still a special subclass of endo-P permutations. But this subclass allows you sort of indecomposable, more indecomposable summands or something like that. So this is a variation of Lassueur's definition. So a couple of things we prove. We define the notion of capped, which is basically saying that at least one copy of K appears. And then we prove that every Dade kg module has a cap, so as a summand which has a zero vertex component. And these zero vertex components are all isomorphic to each other. This was something that without proving this, you wouldn't be able to use this definition. So to prove, to use this definition, you needed to prove these lemmas, basically. And we proved all the necessary lemmas which make this definition work, basically. So at the end of the, you imitate all the things, like equivalence is defined same way, so on. So we define the date group. But the key thing is having summands, which are in the composable summands, more than one copy. So in Lassueur's definition, if you have an intercomposable summand, which is zero vertex summand, you can only have one copy of that. Here we have many copies is allowed, but those many copies all have to be isomorphic. So this is our definition, and this is the we prove that it is equivalent or gives you the same groups as Lassueur's group. So it's not a different group, but definition is slightly different. Okay, I might be running out of time. So let me quickly mention where are most of the date groups come. So most of the date groups come from kernels of augmentation map from a permutation module kx to k. For the P group case, these modules were studied by John Urfer, actually, first time. In the P group case, he proved that these kernels, which he called relative cis-G, he proved that they're endo-permutation modules. So we generalized that to our situation for the finite group case. When S fixed points are empty, this delta X is capped Dade KG module. This S fixed point being empty is also appears in the P group case, but P group case, it appears like if you have only one copy of K, then it's not good, or things like that. Here we have a condition that S fixed point should be empty on the G set. Now, under that condition, you can define these classes omega x, and these omega x classes generate a subgroup of date group. For the S fixed points which are not empty, we declare omega x to be 0, so that we have a well-defined definition for all the x's. This is crucial to have, if you want to work with all indexing set of x for omega x, you need to include the x where S fixed points is non-empty. So by declaring them to be 0, we include all the G sets. And then we define the subgroup, which is called date group generated by relative cis-Gs. This is denoted by d omega G. Now, in the P group case, d omega G plays a very important role. In calculating dg, people actually calculate dg, the date group, by calculating d omega, essentially. In particular, for p odd, in the P group case, ds becomes equal to d omega s. That's the crucial of why we are interested in d omega, basically. In the P group case, ds equals to d omega s for p odd, for example. And for p equals 2, only some small change differences, which you can actually capture with certain type of subquotients. So knowing what the omega is, important part of computing ds. And because it's very combinatorial, comes from G sets, one attempts to first understand the omega. Unfortunately, for finite groups, even this is not clear. So for finite groups with prime being odd prime, there is an open question. It's at the end here. The open question is actually ask if dg is somehow equals to d omega g up to these gamma g's. The gamma g's are the kernels of kernel of the homomorphism from the Lassueur's definition of date group to the Urfer's definition of date group. So omega, this gamma g appears as the kernel of the restriction from the date group we define or Lassueur defines to the definition given by Urfer, which is surjective map. So that kernel is gamma G. And so there is an open question by Lassueur if dg is generated by d omega up to this kernel, which is not answered yet. So it's an open question. But assuming that Lassueur's question has an affirmative answer, one should still focus on d omega g. To understand d omega g is more sort of important part of this. So here's an example. I don't know if I have time to go through a lot of this, but this is an example where we actually show that this for S4, the dg is generated by Z4, and the part that comes from this gamma G and the part that comes from d omega G have a non-trivial intersection. So that showed that you can actually produce a lot of stuff with d omega, even the part in the kernel, the part which is not detected by serial subgroups. You can still get some of these by the omega construction. But I will go to the next one maybe. So to understand the omega, there is a kind of clever thing to do. The clever thing is use the class functions, which we call them superclass functions. These are defined on subgroups, not on the elements of the group. So you take the p subgroups of the group G, all p subgroups. You define a function which gives you an integer to every p subgroup in such a way that the conjugate subgroups have the same value. These things are called class functions or superclass functions, and they form a abelian group. And this is actually dual to some Burnside group, defined relative Burnside ring group or something. So as a group, it's a dual group of the Burnside group relative to p subgroups. The superclass functions have this nature basis, omega x, where the omega x defines such a way that the value at p is 1 if p fixed points is non-empty, 0 otherwise. So this is a slightly different basis than idempotent basis, which will take p to 1 and all the others 0. So this is a little bit different, but this is also a basis. So omega basis is omega x basis is very important. In the again p group case, there was a group homomorphism from these class functions to d omega. So in the finite group case, we proved that there is a similar group homomorphism. This time, though, it has to be defined on only in p subgroups, not all subgroups. It's only defined on p subgroups, and the map to d omega is surjective and well-defined, taking these sub omega x's to the big omega x's. So surjective map means if you can find this kernel, then you found d omega. So if you want to calculate d omega, such a surjective map is what you want, right? You find the surjective map, you just need to calculate the kernel. And kernel can be computable by other ways, right? So you don't need to know d omega to calculate kernel. You can find a way to calculate the kernel by other ways. You know? I have a lot of emails coming. I should turn this off. Sorry. Okay, so this is what we did. This is the strategy to study this group homomorphism and study its kernel, find the kernel, what the kernel could be. So in the P group case, again, the kernel was a very beautiful thing. The kernel was the group of superclass functions, which is class functions come from group actions on mod P homology spheres. So when you have a group action on a mod P homology sphere, on all P subgroups, the fixed point set is still a mod P homology sphere. But the dimension goes down, like smaller dimension. So these dimensions, if you record that on P subgroups, they're obviously equal on the conjugate subgroups. So they give you a class function, superclass function. So these superclass functions satisfy Borel-Smith conditions. These are the conditions found by Borel. It's actually a list of these conditions. I will give it in the next slide. So these conditions forms a subgroup of all class functions. And this subgroup, topological the geometry coming from group actions, turns out to be exactly the kernel of this map. This is when in the P group case, when we proved this with Serge, everyone was sort of, Dade group completed something about KG modules, became same as something comes from group actions and spheres. It was an interesting connection between algebra and topology. So the proof is actually uses some biset functor theory, but you can also try to prove this more geometric ways, which I did actually eventually later on the P group case. I give a proof of this using Moore spaces, Moore G space. But this is the connection between topology and the Dade group. This kernel turns out to be completely determined by group actions on spheres. And so obviously you can sort of ask if in the finite group case, d omega g, CGP, the kernel is something similar. Like, can you compute the kernel by looking at some sort of group actions on spheres, mod P spheres, and so on? What kind of group actions you need to look at? So the Borel-Smith conditions is list of conditions. It's hard to follow or understand what they are exactly, but I just want to show you that these are conditions. And conditions come from things we know, like CP action. The fixed point set is exactly difference is divisible by 2. On the CP cross CP, you have a linear equation called Borel's formula. And the last one is quaternion Q8 one. This is the one Andy asked, like 8 in the Q8 case. The periodicity is 4, so difference should be divisible by 4. So things like that comes from complete topology or the periodic resolutions or whatever you want to think, okay? But Dotzer and Hamlick has a very nice theorem which says that these things not only come from group actions on topological spaces, whose mod P homology is a sphere, but also they come from representation spheres. So you have a group action on coming from representation spheres to their unit spheres. These unit spheres, you can triangulate them, and there's a group action on them as a GCW complex you get. So what they see that the dimension functions coming from these representation spheres gives you entire all dimension functions which satisfy Borel-Smith conditions. Basically, the CB, the kernel, is nothing but the dimension functions or representation spheres, real representation spheres. This is what we find in P group case. So in finite group case, what will you expect? There should be representation spheres. They should give you, on the top dimension, if you have a group action, that should be trivial. So things like that, like you can sort of see how to generalize this to finite group case. So this is what we did. In the finite group case, this is what the dimension function means for representation spheres. In the finite group case, we take G representations. These are real representations, so that when you take the P fixed points, the NGP over P action on it is trivial. So the P fixed points have homology K because of the Smith theory. The fixed point has to have homology K. Actually, this is representation sphere, so it's actually sphere, so homology should be K. But the K may have a non-trivial action of normalizer group. So we want that action to be trivial. These are called K-orientable real representations, and they're denoted by R plus. So what you want that these representations, these are special type of k-oriented ones, their dimension functions give you an entire kernel. And that will finish the computation of the d omega. So dimension functions coming from this. If this is our main theorem, which doesn't say that kernel is exactly this. It says that dimension functions coming from these real representations are inside the kernel. They're not equal. So in some ways, we couldn't prove what we wanted, but we proved one side, one direction of what we want. So the real representation ones sits inside the kernel. And for p equals 2, it is the entire kernel. So for p equals 2, there is nothing else. Just everything is just kernel is dimension functions. For p odd, it's an open question if they are equal. So on p odd, there could be some problems which we don't know how to solve. Okay, a few minutes left, so I will take maybe 2 minutes, 3 minutes extra, if that's okay, just to finish what I'm saying. So this is our main theorem, that the kernel of the map from the class functions to d omega includes the dimension functions of real representations, but may be equal or not, and the p odd. The proof is uses Moore G spaces. So these are G spaces in such a way that for every p fix, for every p group, the p fixed point set is itself a Moore space. Now there is a problem called Steamrolled problem. Steamrolled asks this question: given a GCW complex whose homology is one dimension, concentrated on one dimension, that gives you a KG module or ZG module M. Steamrolled asks the reverse question: given a ZG module, can you find a GCW complex whose homology is exactly given ZG module? This is known as Steamrolled problem, and I guess Steamrolled Moore space problem, maybe. The answer to this question, studied during 70s and 80s, the answer is actually no, not every KG module, ZG module is realizable as a GCW complex. And one counterexample in the general case given by Gunnar Carson, actually. He proved that as long as the group has some CP cross CP in it, you can find a ZG module which is not realizable. So realizability became a kind of question that which ZG modules or which KG modules are realizable? That was a question which people study time to time. There's a paper by Hageber and Benson, Dave Benson. They look at the varieties of the modules to understand which KG modules are realizable. So this, we generalize that Steamrolled Moore space question to a little bit stricter condition that fixed point sets are also Moore spaces. So this is much stronger, of course, to assume that something is a Moore space, but the fixed points also Moore space. So under that condition, we prove that these Moore spaces, whose homology is a endo-permutation module, and in the case actually with the finite group, we prove them these are cap-date KG modules. So in some ways, we're finding the exact class that we need. The class of KG modules which are realizable are these cap-date KG modules. So the reduced homology of an n-dimensional Moore space, whose point stabilizers are all non-zero P subgroups, is a cap-date KG module. And we can also give an exact description of the class in the date group. This class is the sum of omega xi's. So omega is exactly the way it's defined before. relative cis G, and this sum is in the Dade group, which means tensor product. And so the homology becomes tensor product of relative cis G's of its I-dimensional cells, the set of I-dimensional cells. So basically, Dade modules are the class of groups, class of modules, which will be the exact condition if you're searching for more realizable spaces, realizable KG modules, under the condition that fixed point sets are also more spaces. Which is a little bit strong condition, I should say. But so this theorem is exactly what you use actually to prove the main theorem as well. These are finite group. These theorems are for finite groups. For P groups, these were from proved in 2017. For P groups, I had a separate paper in 2017 proving this. So last slides. So the assumption that point stabilizer non-zero is a little bit technical and actually too strong for even covering representation spheres, because point stabilizers of actions on representation spheres are not zero, non-zero P subgroups. So we extend this whole thing into possibility that S fixed points are non-empty. You have to do a lot more work. You have to do a couple of extra things, but you can do it. It works. So you can prove the theorem also for G spaces where S fixed points are not empty. And using that, actually, now you can apply it to the last line here. You can apply it to K-orientable real representation spheres. Now, what happens with the K-orientable real representation spheres? The homology is K. You know it already. And that K becomes the image of its dimension function under the Bouc homomorphism. So that means that the K is zero, so dimension function of the real representation goes to zero under Bouc homomorphism. So that means it's in the kernel. This is how you prove the main theorem, that showing that real representation spheres actually, their dimension functions under Bouc homomorphism goes to their homology. This is how you prove it. So this is actually the end of it, but just before, to summarize just one sentence. So there were things who were proved for P groups. We generalized definition to finite groups first, Dade group. Then we tried to prove things for finite groups. Some things worked, some things didn't work. For example, we couldn't get the kernel exactly, but we were able to prove at least for these Moore spaces that under this extra condition, our class of Dade groups, Dade modules, are exactly the class of KG modules necessary for realizability. And there is an open question now for P odd to show that the kernel of Bouc homomorphism is exactly the same as dimension functions, which hopefully we will prove some point, but not. We don't know how to do it now. So, okay, this is all. Thank you.
Okay, thank you very much. Any questions from the audience?
Hi. So, is it even clear that the Dade group is finitely generated, or is it?
I mean, we take finite generated, so we assume every KG module we look at.
I mean, the representatives are finitely generated, but the group itself.
You mean the group? Sorry.
DG.
Yes. Let me show you. There was one slide which went kind of fast. which show the relation between Urfer's definition and Lassueur's definition. I will go back to that. So there is a short exact sequence which relate dg to the Urfer's definition ds. So Urfer definition gives you G stable elements inside the date group of the 0P subgroup. There's a surjective map. And this kernel is generated by this certain type of isomorphism class of KG modules, which arise from the Greek correspondence of one-dimensional representations of NGS. Okay, so your question, this finite generation of DG, becomes deciding if these both sides are finite generated. Now, for the P group case, it's known that DS is finite generated. I guess it's almost like the computation. So DS is finite generated. G-stable elements will be finite generated. Now, the kernel is one-dimensional representations of NGS. Those are also finite many things, right? So they're the isomorphism classes of these one-dimensionals in NGS are just finite set of one-dimensionals. So gamma G is also finite generated.
Okay, so and in general, is there a coarse bound on like how many summands you expect in this DG, like how big it should be relative to G or something? Is there anything known?
I mean, the complete description of DG is still not there. Like we know the DS, but G stable elements of any group we know may not be that easy to compute. So there is no explicit description of DG. Like we don't know it, that's why we're computing it. But upper bound of summands, number of summands, it may be possible to give some, I mean, like it should be less than the rank of DS and rank of gamma G, right? There's abelian groups. So you can give a coarse upper bound, like bad upper bound. But if you want to go into the G-stable computation, then I don't know if you can give more explicit. Maybe Matthew can answer this too. Anything that comes to you?
I have no additional insight, sorry.
But I mean, you can say the DS, you can tell exactly how many, so its Q rank is known as number of summands, subgroups of S, which are non-cyclic subgroups or something. So there is a rank computation for DS, but it's Q rank. So the summands who are not the torsion summands, torsion part, there is another description in terms of sections. So there are some descriptions of summands with like as abelian group number of generators of DS is known. But then when you need to calculate G-stable, that the summands may change. So I don't know the complete calculation of the G-stable. And gamma G should be possible because it's just a normalizer, right? It's an explicit group, and the one-dimensionals are like homomorphisms to K, right? So you should be able to say exactly what's up. Exactly which quotients will give you that one-dimensionals. But I don't know the complete calculation in that sense.
Thanks.
Do you know the minimal group where the question is still open? Like
which question? The PO?
Question by, I mean, the question that we're seeing.
This one.
Right.
So Lassueur, actually, most of her thesis is devoted to this question. So she studied this question extensively, like 50 page or something. She proves it for solvable groups. For groups is zero subgroup is cyclic. For groups, like goes through a lot of categories. So I don't know, like which she didn't cover. The first thing she didn't cover, which is the small group. I don't know. We approached this question differently from our homomorphism from the Borel-Smith functions, from superclass functions. It's surjective. So we rephrase this question in terms of our sequences. We found that this is equivalent to some other question, which you can ask about the cohomology of fusion systems. But we couldn't prove that either. So this is something we have half work, like we haven't completed. But you could find equivalent versions of this question in terms of how the, I guess, G-stable, taking G-stable elements works. But I don't know which group you should be looking at.
Okay.
Thank you.
Okay, any other questions? Could you go back to the homomorphism, the other question, the Bouc homomorphism that was open?
So the Bouc homomorphism is this, and
okay, so that's mapping to D.
So in the P case, the kernel of Bouc homomorphism, which is described in the short exact sequence, is exactly the image of dimension functions coming from real representations. So the kernel of the map from cost functions to d omega is equal to dimension functions coming from real representations. This is the proof theorem for P groups. Now we want to replace the S with G, and then we want to find the kernel. And the kernel, the candidate we have for the P group, the finite group case, is the image of this map from real representations, which are oriented to these class functions defined on only P subgroups. Now the conjecture or the claim is that the image of this dimension homomorphism is equal to kernel of Bouc homomorphism, kernel of the map to the d omega. The equality is open for P odd. We prove one direction, that image of dimension functions inside. So we can prove that image of dim is inside the kernel, but we cannot show that everything is in the kernel comes from a dimension function. So the other direction is what's open. To be honest, I mean, to proving such this other direction is something very topological. It's about twist on the homology. Like it's a very subtle issue that when you take the fixed points, symmetry says that you get mod P homology spheres. So when you take the fixed points on a real representation, you get a sphere. This sphere on the top homology has K. But that K, what kind of normalizer action it has? So what is the normalizer action on fixed point sets? It is actually a twisted K, some K with an action. Now we cannot prove that they should be K under certain conditions, basically. That is where we lack the proof. We can't prove. These are all happening in homological algebra setting. So the main method to use is actually homological algebra over the orbit category defined on P subgroups. So there's a category, functor category homological algebra going on. So you have to work with orbit category relative to P subgroups and write chain complexes as chain complexes of over the orbit category. That's where the functor homology comes in and so on. So the methods are homological algebra over the orbit category. But we couldn't prove things.
But are you able to verify this for?
P equals 2, we verified this, but we get lucky there because for P equals 2, this twist doesn't exist because you have K and there is no non-trivial action on K. So basically the C2, when you have an extension of CP with a CQ, like CP with a CQ, CQ can act on CP. But you cannot have an extension of C2 with a p-odd prime cyclic group where the p-odd acts on C2. So you cannot twist C2 basically, but you can twist C3 with C2. So when you have a CP with an odd P, and if you have an extension with another cyclic group, the other cyclic group twists that CP. It's possible to do that. But with the P equals 2, you cannot have twistings of C2. This is why P equals 2 case, you can prove these things.
And the other thing is, how does DG depend on the homotopy type of BG? In a way, is it like, does the p-local homotopy type of BG determine the somehow?
Okay, so everything is, we are actually looking at P subgroups in the group. Everything lives in zero P subgroup. So some of these things are determined by only fusion system, which means that it's only depends on P localization of the classifying space. But some things are not. So like the one-dimensionals of NG may not be dependent on just the zero P subgroup. So in some sense, there is a part that depends only on P localization of classifying space, but the other parts will not.
Can I ask another question?
Sure, sure.
So your symmetric group action on this sphere, 46-dimensional sphere, the dimension function of that, can that be in the kernel but not in the image of this dimension function?
Okay, so which action of which group?
The symmetric group action, the S5 action on
now those actions we constructed. First of all, they had isotropy on certain P subgroups. I didn't think about this. So their dimension function wasn't real. So, okay, so there is subtle questions about these dimension functions of group actions on mod P homologous spheres and dimension functions coming from real representations. In the case, finite group case, they are not equal. So, so they're equal up to looking into Grothendieck construction, which means that plus minus like virtual group actions. So suppose you're looking at G spheres. Suppose you created this monoid of joins and dependent on joins. And then you introduce negatives and like Grothendieck construction. So you have a virtual notion. Those virtual ones are realizable by real representations. This is a theorem actually by Bauer and uses these Artin relations and so on. But not every group action on a sphere which has is realizable as real representation sphere. Dimension function is not realizable in general. as a real representation. So here, it won't coincide. The conditions comes from group actions on spheres, but they only coincide if you are in the growth-ending construction, in the virtual sense. So if you are explicitly want to realize one group action with a representation sphere, you may not be able to do this. I think the S5 action is one that doesn't come from the real representation. That's why we had to construct it using 40-page paper. So in that sense, these are all virtual, right? Plus, minus. So I'm not sure that, does this answer your question? Or
Yeah.
but I will think about still what exactly you're saying. But so here, in the finite group work, they are not same things. The dimension functions are real representations, and dimension functions coming from group actions on multiple homologous spheres are not same things. They're different in this.
Thank you.
Thanks for asking the question.
Okay, maybe that's enough questions for the
Yeah.
session before going into the social time. I don't know how different it will be from this session, but okay. Thank you very much for the talk, Ergun. Let me stop the recording.